Gosh, there's a lot of you. Hello. Let's start this session by acknowledging the traditional custodians of the land on which this festival is being presented, the Yuggera people. I also pay respect to Australia's First Nations, who we recognise as the first scientists and custodians of the land and environments and all animate and inanimate things within it. I acknowledge the importance of their legacy, passed from one generation to the other over 50,000 years. And that legacy has had on caring for Mother Earth and contemporary scientific conversations. Let's acknowledge the deep and timeless relationship between country and Aboriginal peoples and Torres Strait Islanders, and also pay respects to the elders of the community, both Indigenous and non-Indigenous, who are here with us today. Good morning, ladies and gentlemen, and welcome to Light in the Solar System. Woo! Now, my name is Tegan, and I'm a health and science reporter at the ABC, but today, with me today, is a very, very smart brain housed in a human body. The brain belongs to astrophysicist Tamara Davis. She studies the elusive dark energy that's powering the expansion of the universe, and she's helped make one of the largest maps of all the galaxies in the universe that we know about, and is now measuring how supermassive black holes have grown over the last 12 billion years. Her work has earned her lots of important awards, which I'm not going to mention now because it'll take too long. But when she's not doing science, she's playing sport, and she captains Australia at the World Championships of Ultimate Frisbee. Professor Tamara Davis!
Hi, everybody! Awesome to see you. It's so exciting to have you all here. We're talking today about light and the solar system. I am an astrophysicist, as Tegan was telling you. I study space. I go out beyond the planets and look at distant galaxies and things even further away than we usually imagine. Now, did anyone here like astronomy? A couple of people. That's good. Lots of hands up. Let's have a cheer if you like astronomy. Anyone like astronomy? That's more like it. So today we're doing light and the solar system. And I was going to start by asking you all a riddle. And the riddle is this. If you can think of the answer, tell it to the person beside you. I can only live where there is light, but I die if light shines on me. Can anyone guess? I only live when there is light, but I die if light shines on me. Okay. A bunch of people yell it out at me.
These guys are too smart. We don't need to do the presentation
are very, very clever. Let's see. Shadows. Does anyone make like shadow monsters? I can't do it very well here. You can't really see very well, but yes, shadows are something that you can only have with light, but they disappear when the light shines on them. Everybody has a shadow. In fact, there's so many lights on me right now that I have about 5. And you can't really escape from your shadow. But the reason that we have shadows is because light travels in straight lines. It doesn't really bend much around a human body like this, and we can see the shadows. Now, does anyone know what light is made of? Yeah, there's a couple of people here. Did you have an answer for what light was made of? Yeah. Atoms. The atoms are stuff that light bounces off, and light itself is made of little particles called photons, which are sort of like atoms, and they can bounce off atoms. But photons are also special because they're not just particles, they're also waves. Turns out that every particle is also a wave, but we'll get to that later. But light comes in waves, and one of the really important features, if we look at has anyone seen a rainbow before? Yes. If we look at the rainbow of light coming out here, the thing that makes the colours different is the wavelength of the light. So have you been to the beach? Seen waves? There's quite a long distance between the waves at the beach, right? takes like, sort of 10 seconds for each wave to come and hit you. But if you're sitting in your bathtub at home and you make some waves, it doesn't take very long for your waves to go and bounce off the edge of the bathtub and come back, right? So waves at the beach have a long wavelength, and the little waves in your bathtub have a short wavelength. So Tegan, can you help me demonstrate? We have a rope here. Now, we were going to try and demonstrate long and short wavelengths of light using this rope. Let's see if we can do it. So a long wavelength would be something that, I'm going to do it in a circle even though it's, if a skipping rope, that's like one wave. This is actually half a wavelength at the moment of light. Or, well, if it was light, something that goes up and down once in there, that's half a wavelength. Okay, we were going to do this with a spring, which would be more effective, but we lost the spring. This, on the other hand, would be a short wavelength. See how the little up and downs are much shorter? And this would be something that was like blue light. So this is taking me a lot more energy to do, right? My arm's going to get pretty tired. I'm not going to last very long doing this. So this is a short wavelength of light, and that corresponds to blue colours. They have short wavelengths, whereas red colours have long wavelengths. Red colours are much more lazy. They have less energy. So if you're thinking about that, thank you, Tegan. If you're thinking about that in terms of temperature, it turns out if you think of something red, we usually think of something hot, right? And if you think of something blue, you often think of like an ice cube or something like that, and that's usually cold, right? Well, it turns out that with light, it's actually the opposite way around. If we have a fire that's all red, it's actually not as hot as something like the gas burner of your stove that burns blue. And the blue there is hotter than the red. And in terms of light, the red wavelengths that were nice and slow and big long wavelengths, they have less energy and are less hot than the blue ones that move really quickly. So that's the wavelength of light. Now, who here, this is a pretty bright light, but what would be the biggest source of light that you guys know of? Well, everybody's hands is up, so yell it out and I'll see if I can understand. I heard stars and sun, and both of those answers are right. Sun is our closest star. So the sun is indeed one of our probably our biggest source of light. It's the stars can be different colours. Sometimes stars are red, sometimes stars are blue, and the ones that are bluer are actually hotter on the outside than the ones that are red. Our star's sort of in between. It's like a pretty average star, and it's a bit more of the red kind. It's not as hot as the hottest types of stars that are out there. Now, if you were to look at the sun and you were to split it up and have a look inside, right in the core, that's where all the action is happening. There's something called fusion going on. People used to think that the sun burnt in the same way as a fire burnt, like, you've got wood and it burns, and that must be what's fueling the sun. But if that was true, the sun would just run out of fuel pretty much instantly. We realized that the sun can't hang around for that long and be burning something like normal fuel, like wood. So what happens in the center of the sun is you get stuff called hydrogen. Has anyone heard of hydrogen? Yes. You bash the hydrogens together, they form helium, and they release heaps of energy in that process. And that's the stuff that fuels the sun. Now, the light that you see from the sun, we're talking about light today, the light takes about 8 minutes to travel from the sun to get to you. But guess how long it takes to get from the center of the sun out to the surface of the sun? Like, this one has a big thing. So tell your friend beside you if you can make a guess at how long it takes to get from the center of the sun and out. I won't get you to yell out the answer to this because I'll probably get too many different answers, but it actually takes a really long time because the sun is so dense. The light keeps traveling and it goes one way and it basically bashes into something, and it goes this way and it bashes into another particle, and it goes this way and it bashes in, and it goes like this to try and get out, and it takes a couple of million years for light to travel from the center of the sun and get out. It's like when you all stand up to leave this theatre at the end of this show, you're going to have to like jostle other people and stuff. You know, there's a lot of people. You can't get out through it. If you were just one light particle trying to escape the crowd, if you were all light particles or the atoms in the sun and things, if you were light trying to escape, you'd have to like bash through everybody in the crowd to get out. And that's what the light is doing inside our sun. It takes a long time to get out. So when you're looking at the sun, you're actually just seeing the stuff from the very surface of the sun. Cool. So if you were to think about the size, we're going to now go to the solar system and do a bit of exploration of our own astronomical backyard. Who are our friend planets that are nearby? Now, to start with, if the sun is that big, how big do you reckon Earth will be? I'm going to give a couple of... We've got some balls here. Do you think... Where should we start? Do you reckon if the sun is that big, do you reckon the Earth is that big? No. Bigger or smaller? Smaller. Oh, bigger. Hands up for bigger.
Do you think the Earth's this big?
That one does look like the Earth, doesn't it? Hands up for smaller? Ooh, okay. Smaller wins. What about this side? Bigger or smaller? Smaller. Oh. Okay. This size? Yes? No? Too small? This size? Bigger? Smaller? I think the biggers were winning there, but I'm going to tell you it's about that big. So if that's the size of the sun, the Earth is only this big. It's really, really small compared to the sun. Cool. Now, when the Earth is in orbit around the sun, and it does all sorts of things. Now let's scale the Earth up. Anyone recognize this? This is us down here, Australia. Now, the Earth orbits the sun. It takes, 365 days to do that, and that's 1 year, right? So if this light was our sun, that means we're going around the sun. You can leave it there. I don't have to spin it. It's okay this time. That takes 365 days approximately. Now, while it's doing that, of course, the Earth is spinning on its axis, like this. And our days and nights occur like this. So it spins on its axis once every 24 hours. So where's Australia? Australia's here. So this is daytime for Australia, and then spins around, and that'll be nighttime for Australia. So while it does the orbit of the sun, it's doing this as well. So that's the difference between the day and the year. Now I have a question for you. Which planet has the shortest day? So that's asking the Earth, it takes 24 hours to spin from Australia pointing to the sun all the way around till Australia pointing to the sun again. Is 24 hours the fastest day? No? Which planet do you think will go faster? Okay, I heard a few people say Jupiter. Jupiter is so big. Do you really think it would spin that fast? You're right. You are right. Jupiter has the fastest day. It only takes 10 hours to spin. So it will have more than 2 days in the time that we have one. Now, at the moment, we're in the transition going between summer and winter here in Australia, right? And the seasons also arise because of the sun. And if you're looking at this, if you'll notice when I was spinning it, I wasn't spinning it directly straight. So the Earth doesn't actually spin relative to the sun directly vertical like this, with the North and South Pole up and down. It spins a bit like this. So it's a bit crooked. And that's the reason that we have the seasons. So if it's spinning like this, you'll notice that Australia here is right here. It's basically pointing at the sun at the moment, right? So is that going to be summer or winter? Summer. And if I point it on, if Australia's on the other side right now, it's still in the same angle, it's just spinning. Is that summer or winter? I tricked you, those who said winter. This is nighttime in summer. So it's still on so Australia's still on the side, the whole southern hemisphere is the side that's closest to the sun right now. And even on the nighttime, I mean it's nighttime so it gets colder because it's nighttime, but it's still summer. You have to wait until you go all the way around the sun and you're on the other side, and now you'll notice that the northern hemisphere is the one that's pointing towards the sun. Does that make sense? So now the northern hemisphere, what does the northern hemisphere have? Summer. And what does the southern hemisphere have? Winter. So we have now winter, and then it will go all the way around again and come back and have summer again on that side. So that's the way the seasons work. There's some weird planets out there that some of them will spin sideways, some will have more or less tilt, so the seasons are going to be different on all of the different planets. Now, okay, you're familiar with the moon as well, and Tegan, I'm going to need your help for some of this. So while Earth is going around the sun, the moon is also going around the Earth. Would you like to be the moon and go around the Earth?
I'd like to orbit you.
Now, I think this moon that's about the right size for this particular Earth, I think. So have you seen different types of moons? You see them different shapes each time, right? And we all know that the moon isn't actually changing shape. We're just seeing it by the fact that the sun is shining on it in different ways. So Tegan, so if we can drop all the rest of the lights so we can just have a look at this one single light from stage at the moment. You can see that if you see that ball from one side or the other, if you're seeing it from here, you're seeing the light from the sun bounce off the ball and come to you. So you should see most of the ball lit up. Is that right? Whereas if it's over this side, the light's shining on the back of the ball and you should only see part of the ball lit up. Is that right? So that's what's happening when you see the moon from the Earth. You're just seeing the moon as it was, where some of the sun is shining on one side of the moon and not all of it that you can see. So if I looked up in the sky and I saw a moon that had light on this side only, where would the sun be? Over that side, yeah. If I could just see a tiny little sliver, I know that the sun must be over there. So next time you go out and look at the moon, you'll be able to go and see, look up at the moon, see which side the light is, and check that it makes sense that the sun is shining from that direction. You know, sometimes you can even see the moon in the middle of the day, and so you can test this out at all times. So that's my challenge for you next time. Look up and see the moon and figure out if you can see where the sun is. It'll often be on the other side, well, at night, obviously, when be behind the Earth. Awesome. Okay. Ready to talk about a bit more of planets? Should we go into planets, Tegan?
You want to do the distance?
Yeah. So, yes. So these were to scale in terms of the size, but let's go to a different size. Now, let's imagine now that the Earth was, imagine that the Earth was a netball. The moon is about that big compared to the netball. And on the scale of this, how far apart do you think the moon and the Earth are? Tell us.
Should we be closer or further?
Further? Okay, put your hands up if we should go further away.
Okay.
A little bit. And put your hands down when you think we're far enough away. Oh, I think we're about. Let's look upstairs.
Last time we better take a couple more steps.
Some of them say a bit more. Okay,
we're so
not
far
many
away.
people have been. Yeah, that's a long way away, isn't it?
Look how small I am. I'm so far away. Do you think I should be further?
Yeah? So, the scale that these are, we should actually be 13.6 meters away. So, should I try? Do you want to try and measure out?
I'll try.
So a meter's about one big step.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13.
So we actually have to be something like this. Yeah. So that's how far we would have to be away. So do you know what this tells us? That the universe is mostly empty space. There's, as big as we think the Earth is, the gaps between the Earth and the Moon and between the Earth and other planets is huge. So there's lots and lots of empty space out there. Cool, okay. Thank you very much. So if we go on, this picture here, interestingly, you might think this is the Moon. This is not the Moon. This is actually Mercury. Now, Mercury is really small. So if we try to compare, we had Earth as this big compared to the Sun before, but if we can't, I won't be able to show you the marble for Mercury if I stick to that. So we're going to do some expanding. So now imagine that there's a sun filling up most of this auditorium. So it's basically going from your head to the roof, like that. Okay, can you imagine that? On that scale, Mercury's about that size. So, and now Earth would be about that size. So a bit bigger than it was before. Okay, so Mercury is actually not that much bigger than our Moon. So the Moon and Mercury is pretty similar, and it has a really cool thing. It spins so slowly on its axis, its day is actually longer than its year. So it spins so slowly that it doesn't go around once. If it was one of these big things, it goes around once more slowly than it does the entire orbit all the way around the sun. So it's a bit crazy, really. A year is 88 days long, but its day is, I think, 176 days long. So it takes a long time. So if you were, imagine if you had to go to school on Mercury. You had to get up in the morning and go to school. You wouldn't get to come home for 176 days. Maybe they'd give you an early mark.
But you'd go through the grades more quickly because the years are shorter.
That's true. Okay, so the next planet out is Venus. Who knows how big Venus is? I'm gonna. So Tegan, can you help me hold up? So let's see. If you take, is it? Okay, so I'm gonna hold a ball up in the air. And you tell me, give us a cheer for which one you think is the size of Venus. So this is just, remember, Mercury was this big. The sun is the size of this room. How big is Venus? Is it that big?
Is it that big?
This big? This big?
They're pretty spot on.
Yeah, this is the right one. So this is Venus. So you'll notice Venus and Earth are pretty similar in size, actually. They're really similar. Some cool things about Venus, though, is that it spins backwards. All planets spin this way, and Venus spins that way. So that's a bit weird. It's also the hottest planet in the solar system. So have you heard of the greenhouse effect here on Earth? How the carbon dioxide in the atmosphere and stuff keeps the atmosphere warm. Well, Venus had a runaway greenhouse effect, and it's one of the reasons that we don't want the same thing to happen to Earth. Do you know, so at the moment in this room it's probably something like 20 degrees Celsius, right? How hot does it have to be to boil water? 100 degrees Celsius. If you were on Venus, it wouldn't be 100 degrees Celsius, it wouldn't be 200, it wouldn't be 300, it wouldn't be 400, it would be 470 degrees Celsius. So you'd need some pretty serious air conditioning. But also you've got like sulfuric acid in the atmosphere and stuff. It wouldn't be a very happy place for humans to live. Okay, we've already talked a little bit about Earth. We know that Earth has a 24-hour day and has seasons. If we go one step further, what's the next planet? Mars. Okay, so we'll do a quick, how big is Mars? We can use the same balls that we had a second ago. Okay, how big is Mars? Is it? It's this one. So this was our size of Earth. Mars is less than Earth. So Mars is smaller than Earth. But it has some really cool things. Despite the fact that it's smaller than Earth, it has the tallest mountain in the solar system. This is Olympus Mons. It's a huge old volcano. It's dead now, but it was an old volcano in the past. Also, if you were on Mars and you had your school day, you would actually have an extra half hour per day, because the day on Mars is 24 hours. So 24 and a half hours. So you've got like half an hour extra compared to what you would have here on Earth. At the moment,
so you could do some extra homework. That's what you do with it, hey?
Yeah, you would have an extra half hour for homework, right? Yeah? That's what you would use it for? No? Okay, so at the moment, one thing that I did that was really, really cool recently was I got to go on TV and host a show about Mars. And it was about us traveling to Mars. And there's something there at the moment called the Perseverance rover. Have you heard of that? Yeah. So it's going around and it was super complicated the way that it landed on Mars. It was crazy. Did you hear about this?
Parachute involved?
Yeah. It like bashed into the atmosphere, did some aerobraking, but the atmosphere in Mars is actually not that thick. It's less than like 1% of what we have here on Earth. So it doesn't slow down enough just by like hitting the atmosphere. So it then deployed some parachutes, and as it was coming down on the parachutes, it like kicked the bottom off and threw that bit away. Then it had some jets coming out the bottom, and then it got rid of the parachute. And then while it was landing on the jets, it pulled out ropes going down to the thing, and it lowered the rover down on the ropes, and it let go of the ropes, and then the thing flew away. And it did this all automatically without any control from humans here on Earth, because it takes about 20 minutes for light to get there, and it was too long for people to communicate back and forth for the 20-minute return time. So that's really cool, but it's now there and it's exploring, sending back really cool photos, and it's doing things like, its main purpose there is actually to look and see if there's life on Mars, if anything could be living there. Not really looking for like green, walking, talking aliens or something like that, but just looking for microbes, the kinds of like tiny little things that you might see through a microscope. Cool, so what's the next planet after Mars? Jupiter!
How big is Jupiter?
So I think we might have to scale up for Jupiter. Do we want to do a test? Pick a couple of balls. Do you reckon this is the size of Jupiter? No? That one?
Nah.
We have a winner. Jupiter is this big.
Wait, where's Earth again?
So that's compared to Earth. Yeah. So it's more than 300 times the mass of the Earth. In fact, if you added up the mass of all of the planets combined, and that includes the mass of all the humans on Earth, if you added up the mass of all of the planets, Jupiter would still be twice as massive as that entire amount, which is really pretty huge. You see that red spot in the picture? That red spot is actually bigger than Earth. And it's a storm. It's like, you know how we have tornadoes and, hurricanes here on Earth? That's a massive storm, but that storm has been raging since we first looked at Jupiter through a telescope. So it's been there for over 400 years. So you know how you go out and, it's rainy one day and clear the next? Well, that storm's been going for 400 years, which is a little bit ridiculous to think about, actually.
Yeah, I'm glad I don't live there.
Yeah. It's one of our nearest neighbours, but it's the first of the gas giants. The reason it's so big is partly because it doesn't have a solid surface. If you tried to land on Jupiter, you would fall through. It's mostly made of gas, so you can't actually see down to the solid surface of Jupiter. And so you'd be able to swim at some point once you got into it. The next of the gas giants is probably a lot of people's favourite planet in the solar system, except for Earth, because Earth is awesome.
It's the fanciest.
The fanciest.
'Cause it wears rings.
It wears rings. What's its name? Saturn. And Saturn's this beautiful planet here. I think you guys can all see it, right? The lights aren't too bright. But you can see some really cool stuff. Remember how we were talking about shadows before? This is taken by one of the spacecraft that was going out and looking beyond Saturn. And see how you can't see part of the rings? So can you tell where the sun is there? It's going to be over there, right? Because the shadows are going through and the sun's not shining, reflecting off the back of the rings. So Saturn is it's another gas giant. I won't ask you to guess this time. It's not quite as big as Jupiter, but pretty big. Still pretty big. One thing it is distinguished for is it has the most moons. Now, Earth only has one moon, right? Saturn has 82. At least 82 that we've found. The number keeps going up because as we look for closer and closer, we keep seeing smaller and smaller things orbiting it. And the rings themselves are the shrapnel, the debris left over from some moons that tried to form and didn't quite form. Now, if you zoom out a little bit further, or if you have another look at this is a really pretty picture of Saturn, but it is also a picture of Earth. Can you see Earth?
Where?
Just up there in the corner. You see that dot? This is everything that has ever happened on Earth has happened on that tiny little dot. And this was something that was taken by the spaceship Cassini. Okay. This was taken by the spaceship Cassini when it was out there looking at it. And so you, if you were there at the time, but I think you were probably too young, this is a picture of everybody on Earth at the time, basically, except some people were hiding behind the other side of the Earth. We might get some questions at the end. So that's a really, really cool picture of Earth. If we zoom in a bit on the rings, Earth isn't in this one, but this is like some pretty things. That's called the Cassini division, and it's 4,800 kilometres wide. This sort of like one of the gaps in the rings. Do you know how big 4,800 kilometres is? It's not quite as big as Earth, but if you put Earth in there, it's about as big as Australia is across. So you could basically fit Australia through that gap in the rings if you wanted to. If we go on to the next one, at the top there's these things that look sort of spiky. This is sort of like a top-down view of the rings, almost. And you can see some shadows coming down from that. The things that are making those shadows are about 2.5 kilometres tall. So they're bits of debris in the rings that have sort of been shaken up such that they're puffed out, and they're about 2.5 kilometres tall, those spikes. Again, pretty cool. The solar system has lots of enormous things that are really fun to look at. Okay, so the next one we have is, that's right, Uranus.
Should we just...
So, does anyone know, is Uranus this bigger or smaller than Saturn? Bingo. This is Uranus. I don't think, you probably shouldn't bounce it. Incidentally, Saturn is so fluffy that if you took all of Saturn, it would float on water. If you had a pool big enough. Anyway, so what's it called? Uranus is the one that does the really weird thing. It spins on its side. So if that's the sun again, it spins. Remember how the Earth sort of spins at a sort of an angle that made the seasons? Uranus spins on its side. So it's a really weird one in that way. And it was the first planet that people found by telescope. The rest of the planets we can see with our naked eye when we go outside. But Uranus, they actually had to find it in a telescope. That was in 1781. They did that, so quite a while ago. But then Neptune was found in an even cooler way. Do you know how Neptune was found? Using maths.
Yeah, maths. Yay, maths.
So,
how do you use maths to find a planet?
So Neptune would be about this big. And the way it was found using maths was that people really carefully observed the orbits of the rest of the planets, and the orbits didn't go in the perfect sort of ellipses that they thought that they should go in. There was something bumping them. So every once in a while the planet would like shift in such a way that you're like, gravity shouldn't work that way. It should just be going evenly around. And they figured out that if there was another planet that they hadn't seen out there, that could be pulling these planets in the weird direction, and it would tell you where and it would explain the weird movements of the rest of the planets. So they did these calculations. Someone said, I reckon that there's going to be a planet at this location, and they said where it should be and how long its orbit should be. And they went out and looked with the telescope and were right. That's really cool, I think. So the power of mathematics. Cool. Now, Neptune was only found a little while ago, and it's only in 1846, and it's only actually gone around the sun once since we've discovered it, because its year is so long. Now, we might need to dim the lights even more so that we can see this one. This is the most distant picture of Earth ever taken. Can you see Earth? Yeah, it's a dot there. So this was one that was made famous by Carl Sagan, who asked them to the Voyager spacecraft was one of the ones that went voyaging out into the solar system and has now passed beyond our solar system. And before it got so far away that it lost the ability to send back photos, Carl Sagan suggested, can we just turn it around and take a picture of Earth? And so they did that, and this is the most distant picture of Earth that was ever taken.
So like the longest selfie ever.
Yeah. So if you had a really, really long arm that went out past the planets, that's what that would be. So we've got a couple of minutes left. So we want to talk about this one, which is not a planet. But I'm sure a lot of you will know that we used to call Pluto a planet, and we now don't call it a planet anymore, we call it a dwarf planet. So I was one of the astronomers who voted to demote Pluto and say it's not a planet anymore. And do you know why we did that? Because we're really lazy. And because we didn't want to make more work for you. So, at the moment, you have to remember the names of 8 planets when you do a test or something about the solar system. If we'd left Pluto as a planet, you would have to learn the names of at least 40 more, and then we would have to change the textbooks every year as we discovered more of them. Because what we discovered is that Pluto is just one of many Pluto-like objects in something called the Kuiper belt. So it's more like a sort of a debris belt, there's a meteor belt around between Mars and Jupiter, and a Kuiper belt is lots and lots of objects out there as well. So if we kept Pluto as a planet, we were going to have to promote lots of other things that are about the same size as Pluto and stuff also to planet status, and we didn't want to have to rewrite textbooks every year and make you learn lots and lots and lots of new names. So I hope you're going to say thank you. But as we learn more about the solar system, these are the kinds of things that we discover. There's so much stuff out there that we still have yet to discover that it's really exciting to figure out what's out there. Now, in the last couple of minutes, we're going to take one step further. If we go out even further, we get to look at something like this. Now, this is not a picture of our own galaxy, because we have not been able to go far enough out yet to look back and take a picture. That would take a very, very long time to get that far away. So this is one of our nearest galaxies called Andromeda, but we think the Milky Way galaxy that we live in is very similar to this one. And if we were in there, we would be about, 2/3 of the way out from the center, looking in. Did you know that one of the cool things about living in the southern hemisphere is that the southern hemisphere is pointed more towards the center of the galaxy. So, Tegan, if you can pretend you're a galaxy, so make a round sort of shape there. So if this is the galaxy, and Earth is like here on the edge, and there's the center of the galaxy. The Earth, actually, I'm going to need a bigger Earth.
You need a bigger Earth. Here, use
Where's
this
the big
one.
Earth?
This one's got Australia on it.
Earth and Australia are pointed slightly so that the South Pole is close towards the center of the galaxy, which means that if you live in the southern hemisphere, you can see most of the galaxy from the southern hemisphere. If you live in the northern hemisphere, you can only see the edge of the circle, not the middle. So if you're in the northern hemisphere, you don't get as good a view of the stars as we do here in the southern hemisphere. So that's really cool, and it's one of the reasons that the Aboriginal people here in Australia they made some of their constellations out of the dark patches in the galaxies, because you can see the Milky Way across the sky, and the dark patches in the Milky Way were some of the characters that they used in their stories, whereas the people in the northern hemisphere used the bright spots of light exclusively because they couldn't see those dark patches as clearly as we can from down here. So, but as we go further out yet again, there's about 100, our sun is a star. There's about 300 billion stars in our galaxy, and there's about that many galaxies in the universe. There's a lot out there. So as you learn more, you'll be able to explore further and further beyond our solar system, learn about not only our galaxy, but the galaxies around us and the entire observable universe, which this picture from the Hubble Space Telescope gives you an idea of. So, with that, I hope you've enjoyed our little talk about the exploration of the solar system. I hope you have a good feel for just how big space is, how empty it is, and also how precious Earth is, because our little planet is really important to look after in the vastness of empty space. Thank you so much for listening, and I hope you have a great time. Thanks, everybody.